Yes, welcome everybody. Today's session is Inventor HSM Efficiency. Now the presentation today was primarily geared up for existing HSM users. If you do not have HSM yet or it's something you're contemplating, please stay with us. You're going to see enough about HSM to hopefully spark your interest a little bit. Again, if you're new to HSM, this is just one example of how we try to help our customers be efficient with products. We don't just want to sell you a product, we want to make sure that you're using it to its full benefit. So this is today's topic. As Ashley had mentioned, there is going to be Q&A available. Tad's monitoring the questions as the session goes on. If you'd rather prefer, you can obviously wait until the end of the presentation to ask a question. I'm sure you may have some questions, so they will be addressed during and at the end of the presentation. In your GoToMeeting panel, there is a Q&A section, or basically a chat window, where you can type in your questions. That is basically how we're going to do that since your phones are all on mute. So there's an example of where to get your questions in. I've got 3 objectives for today. Objective 1 is taking a quick look at adaptive clearing. You may hear a lot about adaptive clearing when you get into HSM. You may not. If not, it's definitely something you want to take a look at. It's a different approach than most softwares on the market. We're going to be looking at setting operation and system defaults to make a system more effective for your use. You may as well have the defaults set the way you want them set to maximize your efficiency. And we're also going to take a quick look at the end at machining templates and how to use templates to speed up your game. Step 1, adaptive clearing. So let's take a look at a quick view of adaptive clearing. I drew up a little part a few days ago in remembrance of Valentine's Day, since it is February. So the part I'm going to be looking at, again, this is not a most elaborate part I can come up with. It's just a quick, simple part to basically compare toolpaths with. As we do a side-by-side comparison, I'm going to be looking at what HSM calls adaptive machining, and I'm going to be directly comparing it to conventional machining. Personally, I've worked in about 9 different CAD/CAM packages. I've seen enough of them out there in the market to realize that they are very similar in the way they operate. We'll talk about some of those similarities. HSM is the first one I've seen with an adaptive machining approach, and I'll try to explain what that is as we get into some live demo. But in order to compare 2 different machining types of operations side by side, we need to set up some constant variables. All my machining for this session of the program is going to be done with a 1/2-inch flat end mill. That's very typically a tool for roughing smaller parts. In all my machining, I'm going to be using a 50% tool step over. That's basically a 1/4 inch, half of the tool. I'm also going to be using a 1/4 inch depth of cut. Again, that may vary depending on the type of material you're cutting. I'm trying to leave the whole material conversation out of this. So basically, my cuts are going to be a 1/4 inch, half of the tool wide, and a 1/4 inch, half of the tool deep. So for the comparison purposes, I'm running everything at 10 inches a minute. I am not using any finishing passes because I don't want to add extra laps on a part to try to buffer numbers or anything like that. Everything being equal. And I'm mainly looking at roughing, getting the stock out of the way, because that seems to be the most time-consuming part of any machining. So again, the whole focus of this particular first topic is tool travel and actual cycle time comparisons. So let me go into the product and give you an idea of different ways to machine. Again, there's my wonderful little Valentine's Day heart. I put a pocket in it to have some cavity to machine. First thing I'm going to do is get into the CAM environment, and I'm going to take a look at the pocket first. As you can tell, let me get you a head-on view of this. It is, well, not exactly a square pocket. It's a square pocket that's got some arcs in it, so it's half square, half arcs. But it's a very typical shape. I mean, parts come in all sizes and shapes. I just tried to pick something that had a little bit of straight and a little bit of curve to it. Now, on a basic machining operation, let me just go in and show you some parameters on this. I am going to point out, as I mentioned in my PowerPoint, all my feed rates are set at 10 inches a minute. You can see I'm using 10 inches a minute for my cutting rate, my lead in, lead out, ramp in, ramp out. Everything is set to 10 inches a minute. That's a constant. If I go to my depth pages, you'll notice that I'm using a maximum step over of 1/4 inch, 1/2 of the tool. I'm not doing anything on multiple depths. It's going to be basically a one cut pass. So if I say okay to this, you can kind of see what the tool path looks like. I'm going to do a quick simulate on it because I want to talk about what you might run into cutting a pocket similar to this one. Now, as I go into this, hit simulate, you'll see I'm just doing a plunge entry and it starts cutting. Now, you might notice this section of the path right here. Even though I told it don't cut any more than 1/4 inch of tool or half of the tool, there's going to be parts in this that where the tool is going to be 100% buried. You can kind of see it taking a full pass there. It comes across. Now it's only cutting a little bit. As we start approaching some of these corners, it's going to step over here shortly. Again, it's plunging the tool 100% there again. Right here, it's basically cutting 1/2 of the tool like I had specified. But as it gets into these corners, you notice you're really taking a deep plunge there. This is very typical of what you run into frequently with conventional machining. Even though you're telling it to only use 25 or 50% of the tool, there's just always going to be corners and shapes where the tool's getting into a little bit more material than you bargained for. This is what most softwares do when they get into machining, is you give them a pocket or profile to follow. That's exactly what they do. They follow that profile. Again, you notice there's a full depth of cut there. You speed this up a little bit. Trying to keep this in the view to where you can see it. Again, all 4 corners, you're going to notice that tool is just literally burying itself. But the good news about this is I'm basically taking 1, 2, 3 laps around this pocket, and in 3 laps, I've got the pocket entirely cleared out. So let's take a look here when it gets done. Speed that up just a bit. Now, if I'm in the simulation, I can always look at toolpath statistics, and I'm going to jot down a couple numbers here. Our total machining time for that pocket is 1 minute and 54 seconds. Total distance traveled is a little over 17.5 inches of travel. So it gives you an idea of what to expect for machining time, roughly just short of 2 minutes. 1 minute, 54 seconds. Now what I'm going to do is take a look at that exact same pocket using what HSM calls adaptive clearing. You can already start by looking at that toolpath and realizing, hey, this is entirely different. It is kind of a unique approach with adaptive clearing. So let me just right click on this. I'm going to go to edit. I want to show you that I'm using the exact same feed rates on the tool. I'm also using the exact same step over on the tool, what they call an optimal load, 0.25, 1/2 of the tool. So everything is basically equal. Let me do a quick simulate on this and let you look at something on the simulation. Let me slow this down briefly, hit play. Again, same plunge as the other tool path. I didn't do anything special about entries. But notice, after the plunge, you're not running the tool across that material. You're only cutting 1/2 of that tool at any given point in time. So it just starts in the middle and just starts evolving or rotating itself out. never cutting more than 25 or 50% of that tool, never cutting more than 1/4 of an inch. As it actually hits the sidewall, you can see it kind of avoid that sidewall. Again, you don't want to gouge your part, obviously. But as it gets into these corners, you can watch the entire tool path, and it never takes more than half of that tool. When it gets down to where it's got to dig in a little deeper, again, never more than half of that tool. This is adaptive clearing. The idea is to approach that stock with the same chip load on every pass. So as it comes in here, you'll see it's basically doing what I told it to do. Don't take any more than half of that tool. So there's a couple corners back there. I did 4 corners in this pocket, so you can basically see it from all 4 different angles. As it comes back across here, you'll see it taking 1/2 of the tool. Hopefully the web video is keeping up with you guys. Again, taking another swipe, 1/2 of the tool. I'll speed this up slightly. Got a lot to show you today, so I don't want to consume too much time just doing simulations. Again, you might notice what it does when it hits the end wall down here. When it makes contact, it starts following the end wall. Then all that's left is obviously the corners. It's taking stabs at it. At no point in time during this entire pocket did it bury the full width of the tool. Okay? Now, what we're supposed to be doing is basically comparing the 2 tool paths, because you guys obviously want to know which is a faster approach. Well, I can pretty much answer that right off the bat. Looking at the initial numbers, the machining time on this one is 3 minutes and 52 seconds. Now, the last one was 1 minute and 54 seconds. So, yes, the time almost, well, let's say it doubled. It took twice as long to cut that. So at initial glance, you may say, well, the conventional machining is faster. Duh, obviously. That is true in a way, because obviously the distance traveled is almost twice as much in this tool path. But I'm going to ask you a quick question. I know you guys can't answer, but which one is going to be better on your tool life? So you might really consider, is it better to just plow that tool through the material, or are you protecting your tool by only taking half of the tool cut? Now, because of that, let me come in here a second. One thing you'll notice, I've been machining for quite a long time, and one thing I've noticed, if your tool path is a good tool path, you can actually run your tool at a faster feed rate. So example, if I go to the tool here and I grab a faster tool, you'll notice this tool is actually running at 22 inches a minute, a little bit over double the speed. I'll say okay. The tool path is going to look the same, but if I go into my simulation, again, I'm not going to make you sit here and watch the whole thing. I'll just run it real quick. You can see it's the exact same tool path, but now let's take a look at the statistics. You'll notice I'm right back to that 1 minute and 54 seconds. So I can run it the conventional way at 10 inches a minute, or I can run it this way at 22 inches a minute and end up with the exact same runtime. Now here's the big question. If I can do this in the exact same runtime, which tool path is going to be better for your tools? Okay, that's just something to consider as far as the differences between a conventional pocket mill versus an adaptive pocket mill. Now, maybe I didn't put out a good argument here. Honestly, if your part is a perfectly square little pocket or a perfectly round little pocket, either method is going to be fairly efficient. You're probably going to have to speed up the adaptive approach to make it equal to the same time as the other approach. But that's if your pockets are normal pockets. I chose one that was a little bit abnormal just to do the demo. So, to give you an example, let me come back in here. Go to the next slide. Little quick summary of what we just saw. The standard traditional 2D pocket, minute 54. Distance 17.56 inches. Doing the adaptive approach, the initial time was 3:52. Distance almost twice as much. But if you're allowed to increase your feed rate, which I can because I'm not burying the tool anywhere. If you increase the feed rate on the first one, I almost put some notes in here and I didn't do it. But if I increase the feed rate to 22 on the first pocket, I'd probably break a cutter because I'm taking a lot of material and I'm burying the tool. But if I increase it on the adaptive program, I can actually achieve the same exact time, even though I'm traveling more distance. So I kind of put this out there as a side-by-side comparison. I know you guys are probably looking for an answer as which way is better. In this case, I'm going to call it a wash. Maybe one is better than the other. Maybe the other is better than the first. I left it out there to let you guys decide. My personal opinion, if it's a perfectly square pocket or perfectly round pocket, it's kind of a wash. When you start getting into unique shapes where you might be burying the tool, I think I'm going to go the adaptive approach, even though it may have a slightly longer runtime. So let's go back to the product again here real quick. Now, that was cutting the inside of this part. Let's take a look at the outside of this part. If I take a look at this outside of this part, I've got a contour machining here. Now on this contour, again, 10 inches a minute, there's my standard. I'm doing the same 1/4 inch cut. Also, because my part is thicker here, I'm doing it in 2 passes, a 1/4 inch each. Again, using a constant, so they're all the same. You can see the tool path it's generated. Now, the traditional contour type machining basically just takes the shape of the part and starts offsetting it. This can lead into some real problems when you get into real life scenarios, because if your piece of stock is square, you need to do those extra laps to be able to cut that square off. Let me just do a quick simulation here and I'll kind of show you what I'm talking about. I specifically went 7 laps around this part, and the main reason is I had to go that far out because even the first pass right here in this corner is fully engaged in that material. You can see that on both these bottom corners. As it comes around, I'm actually taking a little bit more than half the tool here, taking about 2/3 of that tool. Now, because of those 2 corners is why I had to go out so far away from the part. If I come on around, now, where I used to work, I was the programmer, I was the setup guy, and I was the runner. I ran my own programs. So a lot of times if I had a part like this, I'd be standing there at the controller, doing basically what I'm going to try to do here. I'd slow it down as I was getting into material. I'd speed it up. I'd slow it down as I was getting into material. Then I'd speed it up. Oops, there I broke a tool. But as I was speeding it up and slowing it down, trying to eliminate all that air time that's being run. My boss just had a fit every time he'd walk by the machine and see this tool out there cutting all that air. But with conventional machining, that's about the only choice you have. You almost have to do a little air cut because it's following the shape of the part. So I would stand there to control, speed it up, slow it down. And the ones that would get me in trouble, right about here, I'd speed it up and forget that it's taking a little dip there, and I'd end up damaging my cutter. Again, all the drawbacks of trying to manipulate the controller. Now, if you're not the person running the machine, which I know a lot of you just do the programming, you don't actually do the running of the machine, you can't tell the operator, speed it up, slow it down, speed it up, slow it down. So the operator is pretty much stuck with the runtime that you give him. So speeding that on up, you can kind of see it does machine the entire part, and the chip load is fairly constant. Now the runtime on that is 30 minutes and 58 seconds. So we're just shy of 31 minutes. Total travel of 310 inches. Let me close this real quick. I'm going to do the same thing with the adaptive approach. If you notice the tool, again, same feed rate, same 1/4 inch step over, same 1/4 inch depth, everything being the same. The only thing different is the way the tool path looks. Give you kind of a head-on view of that tool path. At first glance, for those of you that have not seen adaptive, it looks really strange to see it when you first see it. I know I was a little bit shocked when I first saw that tool path. But here's the advantage to it. When I go to simulate, you'll see the advantages right away. The minute the tool gets down to position, it starts cutting immediately. And once it engages, it stays engaged. So let me hit play there. Again, you watch the tool come in. It engages immediately, taking 1/2 of that tool, and it stays engaged. So this approach, to put it in layman's terms, is basically saying, don't just outline the part, engage the stock immediately and stay engaged with it. So right here at full engagement, it's taking 1/2 of that tool. As it comes across the bottom, it's taking 1/2 of that tool. Of course, it's got to avoid the part, so you'll see a little bump there showing up. But again, the minute it engages, it stays engaged. It's going to walk around the outside of the part there. Again, 50% of the tool. It's going to come back and clean that little corner off that it left there. It's going to come on around, catch the top piece of the part here. There's that little indent. It's going to come around. Again, 1/2 of the tool. Quick rapid back. When it's not engaged, at least it's in rapid mode. So here you can see it's full 50% of the tool. Going to go ahead and walk around the corner here. It determines which is shorter, to walk around or actually go to rapid. So they do all the thinking for you. Like here, it would take too long to walk around, so it's going to come back in rapid. Slightly speed this up because I know we're on timeline. You can kind of see what the adaptive approach is doing. It's a very fast, efficient way to get material off the part as quick as you possibly can. Now to speed it up, I'm not going to, the second lap's the same as the first, so we'll just speed that up. But let's look at the statistics on that. The first tool path was 30 minutes and 58 seconds. The adaptive tool path, look at that, 13:24. The time is cut in half of what we started at, actually a little bit less than half. So if you're looking at a part that has a little shape to it, and you've got a lot of material to remove, adaptive is way faster than the conventional machining. And the reason it's faster, it has less travel. Instead of 310 inches, it's only got 178 inches. Now, that's just everything identical. Same feed rates, same everything. Now, because I'm guaranteed that my stock removal is never going to take more than 1/2 of my tool, what happens if I edit that and switch this over to the faster tool? Maybe I run it 22 inches a minute instead of the traditional 10. If I do that, take a quick look at the simulation. I don't need to run, I'll just look at the statistics. I can actually machine the outside of that part in 7 minutes. 7 minutes and 6 seconds. So I'm going to ask you, would you rather do it the traditional method and take 31 minutes to do this? Or would you rather do it with the adaptive method and do it in a little over 7 minutes? That's almost 1/4 of the time. Now, inside the pocket, you notice there wasn't that big of a time difference. On the outside of this part, it's a huge time difference. The good news is about HSM is whether you do inside pockets, outside contours, most parts that I've ever machined in life contain both. The best part about HSM they offer you both routines. I've just shown you both offerings. You get to pick and choose which one you want to use. I'm hopefully showing you enough case scenario that you can realize that the adaptive machining only offered by HSM is a very efficient way to get rid of material when the conditions are right. Now, I'll admit, if this heart were just a square box, yeah, your time differences aren't going to be that dramatic. But who cuts square boxes in life anymore? Most of us have weird shaped parts. That's where the payback is. The more unique the shape is, the more adaptive machining is going to save you time. Again, quick recap. Doing the 2D contour, it actually had to take 7 laps. Took 30 minutes, almost 31 minutes. 2D adaptive, cut that down well in half just by changing which routine I ran. Same feed rates, same everything. Now, because you're doing adaptive and you're guaranteed you're only cutting 50% of the tool, maybe I can increase the feed rate. The more you can increase the feed rate, the shorter the time gets after that. But again, even on equal basis, I'm cutting the time in half. If you can speed it up, which you can, by the way, you can cut your time down dramatically, even down to a fourth. With that being said, again, just something to consider. I'm not trying to sway you guys one way or another. I just want you to know that HSM offers both types of machining. I would say if your shape allows, use the adaptive, you will come out ahead. And this is just rawly comparing your feeds and speeds. Another thing that I would like you all to consider is this same adaptive machining is also going to be much nicer to your tool. At no point in time when you're machining with adaptive are you taking more than 50% of the tool. You're going to have a constant chip load, and it's all about your tool life as well. So it's not always about speed. You might want to consider your tool life in that equation as well. So, quick look at adaptive clearing. Let's move on to operation defaults. I know a lot of you signed up on this because you'd like to control some of your defaults. Now, when you get into operation defaults, when I first got into here, I thought the menu was a little bit deceiving because if you right-click on any field in any operation panel, you will see these 5 items here on the menu. Reset to built-in default. Okay, great. What exactly does that mean? Reset to default. Wait a minute. Is it a built-in default or a default? What's the difference between a built-in default and a regular default? Make a default. Okay, I get that. I can make a default. Great. Make all default. Well, what's the difference between a make default and make all default? And then, of course, there's edit expression, which has a hotkey, F2. What about expressions? Where does that come into play? So I thought I'd add a little clarity to all these options, starting with the first 2. Reset to built-in default. It will reset any field or field value or expression to what HSM installed as a default. So if you say reset to built-in, built-in means what was installed on your system, what I call the factory defaults. The reset to built-in default does not mess with or does not do anything with user-defined defaults. It completely ignores what you have defined as a user-defined. It does not change your user-defined. It does not reset any of your user-defined. So the point is, if you do a user-defined, it's safe. The HSM factory default is not going to reset anything you've customized. So that's the good news. Now, reset to default. This is going to reset any field to what your user-defined default is. So if you changed or if someone else changed a number somewhere, you can reset it to your user-defined. Obviously, the user-defined default only works if someone has actually set a user-defined default. We'll talk about what that means. It does not change any factory installed defaults. It does not reset any factory installed defaults. So long story short, there's actually 2 sets of defaults out there being maintained by the system. factory defaults and your defaults. Two completely different sets of numbers. They don't trample on each other. They're two completely separate entities. So things to remember: if you see the word built-in default, factory settings. If you see something that says default or user-defined default, that is your defaults that you took the time and effort to set. So hopefully that clarifies those two. Then, of course, you've got the making defaults. When you click Make Default, it's going to record whatever your value or expression is as your defined user default. The idea on how to use this is to put in your number first, then right-click and say, make this the default. It's very easy to do. If you prefer a 50% tool step over, set it up that way and say, make this my default. Those defaults are saved into an XML format. I'm going to show you behind the scenes as to where all this is getting stored. It is located underneath your user Windows profile. With that being said, each individual user of HSM can have their own specific defaults. So your defaults may be different from your buddy sitting across the hall from you. Okay, so making all defaults. What that does is the same as a user-defined single line item default, but it takes the entire operation, all 5 pages, and makes it all default. So when you see the word all, be careful because it's setting everything related to a toolpath as a default. Again, it saves everything into an XML format underneath your Windows user profile. So the keywords here: single entry, make default, versus all entries, recording all the defaults. You'll see this in the demo. You also have the 5th item there, edit expression. Expressions actually use variables instead of hard numeric values. You know, I could say, I want my tool step over to always be a 1/4 inch. Well, that's fine and dandy if you always use a 1/2 inch tool. But what happens if you change to a 1/4 inch tool? I'm not sure you want your step over to be a 1/4 inch. Or maybe an 1/8 inch tool. You don't want your step over to be a 1/4 inch. It's not going to work. So a lot of times variables are the way to do this. So you could do some examples like, I want it to be 5 times the tool diameter. Or maybe I want it to be 10% of the tool diameter. So I can use variable names and expression names such as tool diameter is one, tool diameter times a certain value. I do have an entire spreadsheet put together that has all the system variables in it, at least all of them that I'm aware of. We can also make that available to you if you want it. So, about setting operation defaults. Let's take a quick look at this and get ourselves into trouble here. Now, to do this, I'm going to bring up another part. It's just a part. I'm not going to do a lot of serious machining on this. It's just here for an example. Little disc with our company logo in it. Now, about machining in HSM. I open up a part. I go to the HSM menu. And a lot of people don't know the shortcuts. I'll show you the best shortcut I can teach anybody. Grab the operation you're going to do. Like I'm going to face mill this. You click one button, face mill. You click another button, tool. You're going to tell it what tool to use. I'm using that 1/2 inch end mill. Third button you click is the OK button. By doing that, I pretty much guarantee you're going to get a toolpath. Now, it may not be the perfect toolpath. It may not be exactly what you want, but it is going to produce a toolpath. Now, if you learn how to set defaults, I can have this toolpath come out perfect every time. So you have to decide what perfect is and make that your default. So, with that being said, let's take a look at what we got here. I'm going to go into this face mill. I'm going to go over here to the Passes tab, and I'm going to change my direction of tool to be 45 degrees. So instead of 0 degrees, I'm going to go to 45 degrees. And while I'm changing that value, you notice I did change it. I'm going to right click and say, make that my default. Make that 45 degrees my default. So when I say OK, take a look at the results. You can see that it's now running at a 45-degree angle instead of horizontally like it was a second ago. So now I basically made that my default. So if I were to come in here and delete this face mill and do the same thing I did a second ago. Face mill, grab a tool, select the tool, and just say OK. Notice this is being machined with my default. It's not using a factory default anymore. It's using my default. So it's just that simple, guys. You can set anything to be your default. Now, let's go back to the edit menu, and let's talk about one other thing. Now, if I come in here and right click on that 45 degrees, I want to show you one button here. Reset to built-in default. Think about that. If I reset it to the factory default, what's it going to do? Well, it's going to go back to 0 degrees because that's what the factory default was. So I say OK. You can tell instantly it's running at that 0 degrees. If I right click on it and delete it, and I make a new face mill, grab my tool and say OK, I'm going to quiz you guys. I know you can't answer, but I'm going to quiz you. When I say make me a face mill, am I going to get the 0 degrees or the 45 degrees? I like to throw those trick questions out there. I'm going to say OK and let you see it. What did I get? Got the 45 degrees because that was the default that I set earlier. Okay, so I want to talk about that. If I go in here, that 45 degrees, again, if I reset it to the built-in default, it goes back to the factory settings. That's what reset to factory default means. You'll notice I can also reset to my default. So I could sit here and toggle back and forth all day long between the factory setting and my setting. Factory setting, my setting. The only time it's going to ever change is if I type in a number and tell it to make that the default. Okay, I'm not going to do it right now. I'm going to leave that 45 as my default. So I can reset it to the built-in or reset it to mine. Does that make sense to everybody? Hopefully it does. Now that it knows that I have a default, where is it storing all this? Okay, where it's storing it, let me get back to my desktop here. Underneath my user profile, you'll see it's users, my name, application data, roaming, Autodesk, Inventor, HSM, defaults. You'll find an XML file sitting out there. It's called face.xml because I'm actually doing a face mill. If I right click on that, I can edit this with Notepad or something like that. If you do anything out here with XML, I'd highly recommend you download Notepad++. But if I edit that file, you'll notice there is a single line in that file that says pass angle expression 45. So that is remembering that that angle is supposed to be set at 45. So if I wanted it to set to something else, I can actually go into this XML and actually change it right here as a programmer, or I can go to HSM and change it inside the program. I just wanted to show you what's going on behind the scenes. Okay, with that being said, let's go ahead and move on in. Now, If you do more than one change, like maybe you're changing the pass extension, instead of 0, I'm going to have it extend 1 inch past the part. So if I go to 1 inch past the part, again, right click, make that my default, say OK. You'll see it's going at 45 degrees, 1 inch past the part. If I delete the face mill, put in a brand new one, again, all I have to do is select the tool, say OK. You'll notice now that both of my defaults are being remembered. I'm going 1 inch beyond, I'm going at a 45-degree angle. With that being said, let's take a look at that face XML. And now you'll notice there are 2 lines of entry in here. One for the pass extension, one for the pass angle. So if you're a programmer, you don't mind getting into XML, anything that this file contains is pretty much going to be its default. Okay, with that being said, let's take this a little bit step further. There are places that I'm going to warn you about and tell you to be cautious with. Okay, if I go in here and let's say I want to make another change to this particular toolpath. If I go in here to my passes page, we've already got our 45, we've already got our 1 inch. Let's say I want to do that in multiple depth cuts. So I turn on multiple depth, I put in a finishing step, and let's say I put in a finishing step down of 20 thousandths, and let's say I want to slow the feed rate down to 10 inches a minute. So I'm making a couple changes here. Again, right click, make default, right click, make default. So now I've got 1, 2, 3, 4 defaults, right? When I say OK to this, you can see the multiple depths. You can see everything going on. I'm actually going to jump out here to the XML file real quick. And you'll see that all 4 line items are there. Okay, so I'm not pulling any punches here, but I am going to show you there is one point where it might fail on you. I don't really call it a failure, but it catches everybody off guard. Excuse me. If I come in here and actually delete that face mill and recreate it, I should get exactly what I have on the screen now, right? Here we go. Delete. Yes. Okay. Face mill. Grab a tool, say OK, and can anybody answer why I did not get the exact same toolpath? A lot of people see this as a failure point. It's not really. What's going on is when I went into that toolpath and I made that change, I had to turn on multiple depths to get to those values. I even had to turn on finishing step to get to those values. Those are not recorded in that XML file. So even though I changed the value and said, remember these values, there's no way to tell it to remember to turn these on. However, I can go into that XML and add those lines of code to do that remembrance. You can't like right click on this and say, remember that. They don't have that in here. But that doesn't mean I can't do it. Example. If you right click, we've done the make default, reset, reset. The only thing we haven't really looked at is make all default. If you say make everything a default, it will capture all these checkboxes and all these other pages. So I'm going to right click here, make all of them defaults. So by doing that, you'll notice I can now delete that toolpath, come back in here to face mill, grab a tool, say OK, and now I have 100% of my defaults. Now, to prove point here, I'm going to go behind the scenes again. I do a quick edit on this face XML. You'll notice there is a lot of lines of code here. There's one line of code I'm going to show you here in particular. I thought it was line 142. There we go. Line 142. There's an expression statement here that says, do finishing step, true. That's that checkbox that says, turn on the finishing step. So, long story short, if I took this line and put it into the XML file that I had there before, it would turn that on and remember that finishing step. So I just wanted to show you what's capable, what can be done, what can't be done. I'm trying to show you everything I can possibly show, but I think you got the idea as to it's all user definable. Now, with that being said, let me go back to my PowerPoint here real quick. Get myself caught up here. Apparently somewhere along the line I closed the PowerPoint, didn't realize it. All right, operation defaults. Again, we talked about what they all do, but I wanted to get to this last page right here. What if you make a mistake? First of all, if you type something in bad or a bad number or anything that it doesn't like, it will turn red. If it's red, it will not let you save it. That simple. So if you see red, that's bad. Correct what you broke. There is a way to correct red. If you can't figure out what you broke, just right click on it and say reset this to built-in default. Problem solved. Any other problems you might run into? A lot of people say, well, what if I saved a whole bunch of defaults and I just royally trashed it? That's simple. If that happens to you, just go back out here to your defaults file and just delete it. If it's not there, you have no defaults. Just start over. So you're not going to break it if you try to do this. That's what I wanted to show you as far as that. One more product thing here, the expressions. Sometimes, example, like the step over the tool. By default, the factory setting on that, it's factory set to use 95% of the tool. So if you grab a 1/4 inch tool, it's going to be stepping over like 230 something. If you grab a 1/2 inch tool, it's stepping over 475. Where I used to work, we never stepped over more than 75% of the tool. Some jobs we only stepped over 50% of the tool. With that being said, right click, I can go to edit expression. That value there is actually an expression. If I go to edit expression, you'll see there's a whole string of expression variables here. The long story short, right there, it's telling it to use 95% of the tool. So if I'm in a company that says we don't do any bigger step over than 50% of the tool, real simple. I'm basically taking the tool diameter and I'm just going to multiply it by 0.50 instead of 0.95. So just by changing that expression, I can set this to be 50% of the tool. I'll say OK. Again, just right click, make that my default, and now it's going to be the default forever. So just give you an example. There's the built-in default. There's my default. Factory built-in, 95%. Mine, 50%. So even though there's expressions in there, if you take a look at them, chances are you can set your default. But by using an expression, I now have a default there that's going to work with any size tool I pick up. So my point is, why not set these to your preferences, and then you'll be able to go crazy on every toolpath and not have to really edit anything. One quick last thing here. Machining templates. About to run out of time here. Machining templates are very similar to setting your defaults. Machining template is not stored in the same location as defaults. It's stored in a different place. I actually have 2 locations listed here on the bottom of this slide. It stores the complete operation, including the tools being used. So it's kind of like setting defaults, but it's operation specific. With that being said, let me jump out to the product real quick. And I'm going to open up this part. Give you an example on this. Now, I've already machined this part. I did a face mill on it. You might notice it's a double lap. I've got a rougher and then a finisher. So I consider that like the perfect face milling operation. I use adaptive on the outside of this part. I've got a certain step down that I'm using. I've got a certain finish pass at the bottom that I'm using. It's staying 20 thousandths away from the part. So I come back and actually do a little cleanup profile. I do adaptive inside roughing. You can kind of see this is a similar shaped pocket to what I had a minute ago. Step downs, everything I've got set, I consider perfect defaults. And again, because I've got the roughing staying away from the wall, even do a little finishing path on the inside. I've got a chamfer mill going around cutting all the chamfers on the top. I've got some drilled and tapped holes, so I've got a little spot drill. Then a number 7 drill and a 1/4-20 tap. Okay? You can basically take an entire machining operation, an entire machining setup, not just one operation. I can take all of these, the whole bundle, just right-click and store that as a template. I've got all kinds of templates out here. I've got, what I'm doing here is like a complete part. And I've got 4 different sizes set up. The reason I have 4 different sizes, they're all set up with 4 different cutter sets. The bigger the part, the bigger the cutter set I'm using. The smaller the part, the smaller the cutter size. So to give you an example, I would just save this as a template. Now, why would I do that? Real simple. This part, along with other parts, if they look the same, if they smell the same, if they behave the same, why not machine them the same? So I'll give you an example. I'm going to go ahead and close this part out. I'm going to open up another part that's similar to it. Looks similar, right? Yeah, great. There's absolutely nothing identical about it. But this part has an outside. It's got pockets. It's got some 1/4 tapped holes. It's got a double pocket on the inside. It even has some counterbore holes in here. So how can I take a part that's completely different and machine it with the same set of tools and the same operations? It's real simple. Right-click over here, create from template. I'm going to grab the complete part template. Now, I can grab bits and pieces of it, or I can just grab all of it. So I'm just going to grab all of it. Now, it saved it, it brought it all in, and now I've got 100% of what it had in that other part. The only thing the software does not do for you is it doesn't know how to select entities on your part. So what you have to do is basically go through and pick what you want to machine. Like the face mill, that's easy. Edit that, say OK, because the part only has one face. Done deal. Okay, the outside roughing. If I edit that, I just go to selections, and I need to pick, helps if you don't uncheck the arrow. All I need to do is pick the outside. It knows what to do with the adaptive machining. So it's going to machine the outside of the part. Again, step overs, step ins, everything it remembered from the other part. Now that finishing contour, easy enough. All I have to do is say my selection is that profile. There's the finish pass. Again, inside, edit that. Just make my selections. Now, the other one only had a couple pockets. This one's got a lot more. That's okay. All I got to do is select them. Even a step pocket, I can just select both levels of it. And by doing so, I now have all the pockets roughed out. Give the software a chance to catch up with me here. Now, along with that, while it's calculating, I can actually keep on working. I'm going to edit the inside finishing. Contours, again, because I'm doing a cleanup pass because my roughing was staying 20 thousandths away. want to take that last 20 thousandths off. So again, just come in, pick the insides of these pockets. It doesn't matter how many of them you have or what order you pick them in. Just let it come in and finish those. Again, the other part had a chamfer on it. This part doesn't have a chamfer. That's all right. Right click, delete that. I don't need it. If the part doesn't have a chamfer, then I just don't worry about it. Now, spot drill. Again, spot drill is going to be easy. I just need to pick that spot. Whoops. That one. I should have zoomed in on that. So there's my spot drill. My number 7 drill. That's going to be the deeper hole. There we go. And then the tap. All I have to do is go to my geometry, pick the face that's being tapped. So if you think about what I just did there, I took a part that is completely different from the first one. I went through 8 machining operations, 9 if I'd have kept the chamfer in there. And now I have a part that is completely machined 100% off of defaults. Let me grab the whole setup and simulate that. And then I will open up the floor for questions. I have been monitoring the panel. Hopefully Tad has. But hopefully I've shown you a few things that you can use to speed up your machining operations. You'll notice it's using all my defaults. It doesn't matter what the shape of the part is, how many pockets it has, how many profiles it has. I can basically use that complete part template that I stored and use it on a wide variety of parts because it's got all my favorites built into it. So I just completely machined a part in under 2 minutes. It's kind of hard to beat that for efficiency. All right. Let me open up the question panel. I'll answer any questions. Wow, there's several questions have come in. I noticed Micah was asking a question. Those template, or basically those defaults I was putting in the public documents, same thing with templates. One thing you can do, this is a cute little Windows trick. The question is, can I have that user profile location on a network location somewhere so all my users are using the same defaults? Let's talk about defaults and templates because the answer is yes. One cute little trick you can do is go to that user profile defaults folder, put a folder shortcut there that points to the network. That way when somebody says, go to templates, they click one folder and they're going to be at that network location. I haven't actually tested to see if defaults work that way, but I have done that specifically for template purposes. So hopefully that will answer the question. Yeah, somebody just put a comment. Oh, okay. Used to do that in the good old days with a little shortcut in a batch file. Yep. Same basic principle if you've been there before. Wow. Question just came in. Kind of a loaded question. I'm not going to answer that verbally because I don't want to get into competitive conversations. So we may take that one offline, Robert. Looks like Tad took out most of the questions that were coming in. Anybody else before we close out the meeting?
Yeah, Clayton, I've been answering the questions, sending privately. I don't know if I messed that up and maybe you weren't seeing those, but I think we're good.
One last question just came in, Tad. Can we do the same thing for turning? And the answer is yes, you can do the exact same thing for turning. I think that's most of the questions, Ashley. Again, if anybody else has questions, even after we close this session, you can obviously email us at any time. Just contact your sales representative. They can get questions to myself or Tad or anybody else in the company. We should be able to take care of any questions. Just let us know.
Okay, thanks, Clayton. Yes, that's what I was going to just tell everyone. You can also just reply to that GoToWebinar email or reminder you received, and we can get those forwarded to whoever. Once again, if you could take a few moments to fill out the short survey, it will just pop up as we close down today. Thanks for attending, and have a great day, everybody.